The biggest enemy of a fast chemical reaction isn't usually the starting materials. It's the byproduct trying to kill your reagents. Imagine you're trying to couple an amine with an acid chloride to make an amide. This acid chloride is incredibly reactive, which is exactly what we want. But notice what happens the moment they meet. Every time a bond forms, a molecule of hydrogen chloride, or HCl, is born. As you can see here, this cloud of HCl byproduct is hungry. Before it can even leave the flask, it finds the nearest unreacted amine and protonates it. Our nucleophile, which started as a fast-moving scout, is now a bulky, positively charged ammonium ion. It's been effectively sidelined. In a standard setup, you'd have to use 2 equivalents of your expensive amine just to get a 50% yield, because half of it is busy acting as an acid scavenger. But what if we had a professional bouncer to handle the trouble? This is where the Schotten-Baumann reaction comes in. To solve this, we don't just use a single flask of solvent. We use a biphasic system, 2 layers that don't mix, like oil and water. In the organic layer, we keep our acid chloride. In the aqueous layer, we dissolve a strong base, like sodium hydroxide. Now, watch what happens at the interface where these 2 layers touch. The amine stays mainly in the organic phase, where it's free to attack the acid chloride. But the moment that pesky HCl byproduct is formed, it's instantly pulled into the water layer. Think of the aqueous phase as a chemical sponge. Once the HCl enters the water, the sodium hydroxide neutralizes it immediately. You might wonder, why doesn't the sodium hydroxide just attack the acid chloride directly and turn it back into a carboxylic acid? That's the beauty of the biphasic setup. The acid chloride stays tucked away in the organic layer, shielded from the base, while the reaction happens right at the border. Let's look at the electrons to see how this push and pull works step by step. First, the nucleophile, our amine or alcohol, attacks the electrophilic carbon of the carbonyl. Notice how the pi bond breaks, pushing electrons up onto the oxygen. This creates what we call the tetrahedral intermediate. It's a high-energy, crowded moment in the reaction. Next, the oxygen wants its double bond back. As the electrons kick back down, they force out the best leaving group, the chloride ion. But the nitrogen is still carrying an extra proton and a positive charge. This is the critical moment. Instead of another amine molecule coming in to deprotonate it and becoming dead weight, the inorganic base in the water layer does the heavy lifting. The base mops up that proton, regenerating a neutral, stable amide and leaving our remaining reagents free to keep reacting. By using this scavenger system, we get incredibly high yields at room temperature with a very simple workup. You don't need fancy catalysts, you just need to keep the trash away from the workers. The Schotten-Baumann reaction teaches us a vital lesson in synthetic strategy. Sometimes the best way to drive a reaction forward isn't to add more energy, but to strategically remove the one thing standing in its way. By using a 2-phase system to neutralize byproduct HCl, you ensure that every molecule of your nucleophile counts.